Sometimes the most brilliant engineering solutions are the ones hiding in plain sight. Take this idea from a US patent. It tackles a super old problem. How do you make an artillery shell fly farther without packing in any more fuel? And the answer? Well, it's surprisingly simple, and it's got nothing to do with rockets. So here it is. It's a normal artillery shell, but it's got this kind of strange fabric cone popping out the back. It almost looks like an afterthought, right? But the big question is, how can a simple piece of fabric completely change how a projectile flies, especially one moving faster than sound? The physics going on here is just fascinating. Okay, to really appreciate how clever this solution is, we have to understand the problem first. And for anything moving at high speed, the big enemy is drag. But it's not just about being pointy at the front. What happens at the back of the shell is just as critical. And the main villain of our story is something called base drag. See, as the shell rips through the air, it leaves this messy, low-pressure area right behind it. Basically, a partial vacuum. And that vacuum literally sucks the shell backward, fighting its momentum and just robbing it of range. A really easy way to picture it is like this. Imagine the shell is dragging this invisible anchor behind it. The bigger and flatter the back of the shell is, the bigger that anchor is, and the more it slows everything down. The whole goal here is to cut that anchor loose. And this is where the genius of this patent really shines. Instead of some complicated rocket motor or just jamming in more propellant, the inventors figured out a purely mechanical, purely aerodynamic solution. The patent itself gives us the perfect analogy. They call the fix a boat tail. And it makes total sense, right? Think about the tapered rear end of a boat. It helps the water flow smoothly around it, which creates less drag. Well, that's the exact same idea here. Tapering the back of the shell helps the air flow more smoothly, which shrinks that vacuum and weakens the pull of that invisible anchor. And this is a fantastic illustration of the whole idea. On the left, you've got the mechanism in its stowed state. It's tucked away nice and neat inside the base of the shell so it fits in a standard cannon. And then on the right, you see it deployed, creating that super important boat tail shape while it's in the air. So how does it get from one state to the other all by itself? The real magic here happens in two stages, and it all kicks off at the moment of launch, using the raw, violent energy of the firing itself to power the whole thing. To really get how this works, we just need to meet the three stars of the show. We've got a piston, a chamber for storing gas, and of course, the fabric fairing that does all the work. Just keep an eye on how these three parts work together. The entire sequence is this beautiful three-step dance powered by physics. First, it captures gas from the launch. Second, it waits for the outside pressure to plummet. And third, it uses that pressure difference to pop open. Let's break that down. All right, so the instant the propellant ignites, the shell gets hit with thousands of pounds per square inch of pressure. This little device very cleverly siphons off a tiny bit of that super high-pressure gas through a small intake, and it stores it in that sealed chamber we just talked about. It's basically bottling a tiny piece of the explosion. Now for the really slick part. The shell is now flying out of the barrel, and the system is armed and ready to go. The trigger for this thing isn't some timer or a fuse, it's just pure physics. The very instant the shell clears the muzzle of the cannon, the world behind it completely changes. It goes from being in a crazy high-pressure environment inside the barrel to being in the regular, low-pressure open air. So this is the absolute key to the whole thing. The shell now has a pocket of extremely high-pressure gas trapped inside its base, while at the same time, the air pressure outside its base is suddenly super, super low. That difference in pressure is the engine that drives this entire system. And this graph from the patent is the real aha moment. That dotted line, number 90, that's the pressure that's trapped inside our little chamber. You can see it stays way up high. But now look at the solid line, number 88. That's the air pressure right behind the shell. It spikes, and then the instant it leaves the barrel, it just craters. That massive gap between the two lines, that is pure, raw mechanical force just waiting to be used. And that force has only one place it can go. The high-pressure gas inside slams against the piston, shoving it backward against the much weaker atmospheric pressure. The piston shoots out, pulls the fabric fairing with it, and the whole thing locks into its final aerodynamic boat tail shape. And it all happens in about 20 milliseconds. Just incredible. So after all that clever physics and slick engineering, what's the bottom line? Why is a simple mechanical device like this actually a pretty big deal? Well, let's just tick off the advantages. It extends the shell's range by slicing through that drag, and it does it using zero extra fuel. It's totally passive. It's powered only by the launch itself. And maybe the most important part is that because it's a simple kit, you can retrofit existing shells. You can take this huge stockpile of standard ammunition and almost overnight make them smarter and give them longer legs. This whole invention is just a masterclass in elegant design, using the raw laws of physics to create a smart, passive system. In a world of GPS-guided missiles and billion-dollar weapons, it really makes you wonder, what other brilliantly simple, game-changing ideas for so-called dumb projectiles are still out there, just waiting for someone to think of them?